But for now, we're going to be moving on to the second section of the stream. Well, I guess third if you count the stock market. So, for this new section, we are going to talk about motivation. But we are not going to talk about the normal kind of motivational talks, I guess. There's one thing that I've found is that in the realm of engineering, there is a lot of stress and a lot of work that needs to be done, um, which can sometimes cause depression or perhaps a slum of your workload where there's a lot to be done, so you don't do any of it. And I just wanted to kind of shed some insight on the whole idea of motivation and getting the job done. I hope to provide this insight in a way that is acceptable by the engineering community. So we're not going to be talking about all of the hocus pocus of certain motivational speeches. Instead, we're going to be talking about friction and energy. Not sure why I didn't capitalize energy, but I capitalized friction. When it's funny that we normally talk about friction as a small f, but let's ignore that. We will start by talking about friction. So, if you will recall from your physics class, or perhaps dynamics, or I'm trying to think of other things that would involve friction. Yeah, I feel like dynamics is the big one. Um, you will know that there are actually so first off, I should show the equation. So, as I mentioned, we have a small f, and then we are going to have our normal force. That is an a, not an n, times some constant k, um, and we're gonna put that. And so this is a funky way to put it, but um, this constant k is something that we find experimentally. So with friction, when there are two different scenarios that are the main scenarios we come in. So to get an idea for this, we really have to see what's happening on a micro scale. So if we have, per se, a box that we are trying to slide across a surface, and I'm just going to kind of garnish this box slightly so that we can color it in and make it look nice. So we have this box and we have some surface that we are sliding this box across. We are applying some sort of force, and this force actually has nothing to do with the friction at all, other than the fact that the friction is opposing it. So if we increase the force, the friction doesn't change unless we change to a different scenario. This normal force is actually the weight of the box in this scenario, pushing down and making this connection between the bottom of the box and the floor that we are sliding across. But if we take a magnifying glass to this section right here, and we just kind of zoom in, what you'll find is that if we have, so I'm going to draw like this, and this is going to be like oh, sorry, I didn't mean to complete it. So that's going to be a chunk of the box, and this is going to be a chunk of the ground, which I have once again not done what I wanted. The box is going to have some irregularities to it, because everything isn't necessarily perfectly smooth. You can only achieve perfectly level surfaces if you were perhaps a super genius, but then the floor itself also has these irregularities. Now, unlike my picture, they don't necessarily match up in sequence, but just picture that this is some arbitrary amount of spikes and bumps that are not significant enough to show up on a macro scale, macro in that case. So this is our box, and this is our ground. And so, like I said, there are two different things that can happen here. We can have one case where the box is currently sitting where there are a lot of well, let me grab this. Let me see if I can do this. So, actually, I don't know why I'm doing that. Why don't I grab the box? Because that would make more sense. And we're going to do a transparent selection. Yeah. So then if I grab this, because I used white, other than the fact that I missed that corner. So there's two different situations. The box could be sitting here, where it's kind of locked in place by these different bumps. And when you push to the side, what happens is that in order to actually start moving, there is something we have to overcome, and that's the geometry of this micro scale. So you actually have to go up a little bit to get over these little bumps and dislodge them. So this is something that is called the static friction. So we're gonna call that F(s). So in that case, the static friction is saying that we haven't started moving yet. So with the static friction, it's difficult to get something to start moving. But what's interesting is once you overcome that little problem of the static friction, we get to something called the kinetic friction. And what's nice about the kinetic friction is that since we have already overcome our original problem, we are now sliding over the tops of these bumps, much like if you hit the right speed in a fast boat. You can skip over the tops of the waves, and you don't get that turbulence that you do. With the kinetic friction, we are now moving smoothly across this micro scale topography, and it allows us to use less force to continue that movement. It's something that's a little confusing with inertia, because if we think of inertia just resists change to speed. So we would imagine that it would resist in the initial state because it doesn't want to start moving. But then once it starts moving, we would imagine that it would take the same amount of force to stop it from moving, in a little bit. So it obviously, if you apply the force over a certain period of time, then you have to add that up and calculate the energy. But ignoring that, so how does this apply to motivation? Now, I bet you can probably guess where I'm going at with this, but basically what I'm saying is that with when you have a long list of things to do, or perhaps you haven't done something in a while, and in my case, this happens a lot with coding. So if I'm trying to code my game, then perhaps I've gone on vacation or something, and when I come back, I haven't done it in a while. So it might take a little bit more effort to actually get myself to do that. But once I get the ball rolling, things really start to click because I'm in the right mindset and I'm actually working on what I'm trying to do. So I can see the end goal. So that is my relation to our static friction and our kinetic friction. We're gonna do an F and a K. So the static friction is the situation where you perhaps are laying on the couch and you have 3 assignments to do, and you are just trying to think about which one you might want to do first, or prioritizing, but what's really happening is that your mind is just not moving yet. And so my suggestion is to just do something, even if it's not the homework, even if it's just a little task like perhaps going and putting the dishes away or something like that. Just get the ball rolling of being productive, and things will start to be in that kinetic mode where perhaps you're already in the mindset of working on something and you can overcome that initial. It's a lot easier to continue that trend of momentum and motivation. So I said that there were two different topics I was talking about in terms of motivation. The second is going to be energy, and so energy, the way I'm explaining this is somewhat similar, but uh, I'm going to try to give a slightly different scenario for how it's used. So, in terms of energy, we're talking about reactions. And so, if you think about a situation, perhaps if we have the reaction for water between hydrogen and oxygen, so we have H2 plus O2 is goes back and forth, I guess, kind of sometimes with two H2O, and we need two of those. So this is the equation that is used to explain the creation of water. Now, in real cases, sometimes when we don't usually have like perfect situations like this, but what we can explain is the energy states of the reactants and the energy states of the products. Sorry, I don't know why I blanked there. And we can create a little graph of explaining what happens during the reaction. Now, in the case of water, which probably is a bad example, we we have these states, and I guess it's not that bad of an example because there are situations where this would work. So basically, the picture for this graph that I'm trying to picture. So this is time, this is energy, um, is like so. And basically, what this is if you remember from perhaps the second law of thermodynamics, um, the system pushes everything towards a lower energy state. Like everything wants to be spread out. So if there's more energy, it's kind of like being at the top of a hill. If you're at the top of a mountain and you put a ball there, it's gonna go down. That's because of gravity, but it's similar. The potential, the energy potential in the chemistry is there, and we want to be in a lower state. But what you'll see in this picture is that the gradient actually initially goes up. And the reason for this is that it's currently in a stable state. And in order to make the reaction, we need to unstabilize that. And what's happening, and so water isn't actually the worst example because we have two diatomic atoms. These atoms really want to be together. And in the case of the hydrogen, that's not too bad because the hydrogen's already together. But we really need to break these atoms up um, individually so that we can make the new molecule. And so that's going to take some initial energy. But once that energy is put in, we can start going back down this gradient. And what happens is it actually gives off more energy than you put in. So what this would kind of go towards, and so I mean this follows suit with water. If you put hydrogen in oxygen and then give it a spark, it will ignite quite vigorously and turn into water. Um, so this is a situation where we have certain input characteristics of the environment. So this is ICs or something like that. And this is the graph that we're getting. And in this current situation, and in this initial environment, there is this gap to get, or sorry, not a gap. There is this mountain we have to climb in order to get to the situation where things kind of just flow on their own. Now, what I would suggest in terms of reaction energy is that if we change the initial conditions a little bit, we can find a situation where things are actually in our benefit and it's easier to accomplish a task. So what you may find is perhaps that if the temperature were high enough, this reaction will take place automatically once the two reactants are introduced to each other. And that is because the graph now no longer has that hump and just immediately starts going down. And so that's what I mean by changing the initial conditions. In terms of the reaction, if we change perhaps the temperature, pressure, the amount, the proportions of the different materials and reactants, perhaps if there's some sort of catalyst available, then there are situations where these reactions will just happen on their own without having to introduce some sort of energy to the system. And so in terms of motivation, what this plays out to is perhaps you are in a situation where you are actually attempting to start your work, but it's not necessarily working. That's probably a terrible sentence, but what I would suggest is you should change the situation, because obviously something that is currently happening isn't working. Now, this is a dangerous idea, because if you are actually just procrastinating, you can use this as an excuse in order to continue procrastinating. But I live by the philosophy that if you are tired, it's not worth it to attempt to put in the work, because you're just going to get unsatisfactory work out of yourself. If you do have the time, it may be worth the risk to take a small nap and produce possibly less but more quality work. It has been found that people who try to drive while tired tend to do very poorly in terms of reactions and actually thinking about what they're supposed to do. So a situation where you are initially tired may not be the optimal situation for trying to complete a task. So changing those initial conditions can significantly improve the actual outcome and the amount of effort needed to reach that outcome. So that is pretty much everything for my motivational speech, I guess. And I'm going to be moving on. We are going to do the random drawing section. So I'm going to